This segment on energy problem solving will be a little longer than you're used to, but there's a lot of stuff that's going on before a problem can be assigned for you guys to work out. So here we have an incline, pretty standard, and we want to know the final velocity of a box that starts up here. Here's my box at the top of the incline, and we're just going to let it go. Friction is an incline, so we don't have to worry about friction, coefficients of friction, anything of that. It has a mass of 5 kilograms, it slides 6 meters, and it makes an angle of 42 degrees to the horizontal. Right here, this is our 42 degrees, and the distance, the displacement, this 6 meters is the length along the hypotenuse. The system is the block. There are no external forces, and we will use the conservation of energy. The gravitational force is wrapped up in the gravitational potential energy as part of the system. And first of all, let's identify what types of energy are involved here. We've dealt with 3 types of energy so far: gravitational potential energy, kinetic energy, and elastic potential energy. For this problem, you can see we have a block at a height. There is no spring around, so there is no elastic potential energy, and we know that the block's going to move, so there will be kinetic energy. So we take our conservation of energy equation, where the initial energy has to equal the final, and check the note out down here. We're just going to save a little on subscripts, and if we don't put an F, that means we're talking about the final energy. So we cross out elastic potential energy on both sides, and we have kinetic energy initial plus gravitational potential energy initial will equal the final sum of the kinetic energy and gravitational potential energy. And you can see we've got the angle in here and the displacement from the last side. First thing you do with any problem, label everything you can so you get a good sense of what's going on. We'll now start substituting in algebraically our values for the 2 types of energy. We have kinetic energy, 1/2 mv squared plus mgh, so this is initial. That has to equal our final. Now, we don't have the height. We were given the displacement right here, and we were also given the angle. To find the height, we use a bit of trigonometry. We've done that earlier, and what a good way to remember this is the side opposite the angle here is always going to be the hypotenuse times the sine of the angle. So in this case, the height will be d sine theta. 6 meters is our d, 42 degrees is our theta, and we wind up with h0, where the object starts, is 4 meters above the horizontal. We also know our initial velocity is 0 meters per second because it's not moving, and we know our final height will be 0 meters. And here's what we want to find: the velocity at the bottom of the incline. Almost time to put the numbers into the equation, but first we want to solve it algebraically for the variable we're looking for. This helps shows the teacher that you know what you're doing, and then if you do make a mistake at the end, it's easier to correct if you've just made a mathematical error. Or if the problem then changes and you have a longer slope or a different angle, you can just work with the end. You don't have to worry about keeping track of numbers until you get to the very end. So here we go. This is where we started up here. We realize that at the bottom of the hill there's no no potential energy, and at the top of the hill there's no kinetic energy. So we divide out the m's, they cancel. We have gh0 equals 1/2 v squared. Now again, don't put the numbers in yet. We want to find velocity. So we isolate v. We find out it's equal to square root of 2g times h0, which is our initial height. Now you can put the numbers in right at the bottom here, and it comes out with an answer that the velocity at the bottom of the incline is 8.9 meters per second. Now let's make it a little trickier. We're still going to deal with an inclined plane, okay, with an angle theta here, but this time we're going to put a spring at the bottom. And we're going to take a box. We're going to start the box up here, okay, this dashed line here. We're going to push the box down, compressing the spring a certain amount. Then we're going to let it go. Again, we're not going to worry about friction. And our problem this time will be to find the velocity of the box when it rises back to where it was first compressed, a height of delta H. So in other words, we push it down, we let it go, and it should come right back up to here, and then we want to find what's its velocity at this point. What energies do we have to consider? We're going to look at this again in two places, the initial and final conditions. When we compress the box, this of course is a mass spring system, the box will have elastic potential energy as the spring has been compressed. It will have a certain amount of gravitational potential energy. As you can see right here, it is still above the ground, and it will have no kinetic energy. After we let it go, it rises up to this point, and at this point the spring loses contact with it. This would be the equilibrium point of a mass spring system where we know the velocity is at a max, but it has no more potential energy. So at this point here, the final point, it will have kinetic energy, it'll have a gravitational potential energy here, and it'll have zero elastic potential energy. So our conservation of energy equation, which lists all the different energies, simplifies to the initial elastic potential energy and gravitational potential energy when it's at this spot right here, and then when it is released and it loses contact with the spring, it will have a kinetic energy and a GPE at this point. Before we proceed further with the solution, just think how hard this problem would be to solve without using the conservation of energy. Once the object is released and it starts moving away from the spring, the force is no longer constant. It will require mathematical integration or calculus to solve. Again, the spring force is F equals kx, so that will be changing as it's moving away. The x value changes, the force changes. Free body diagrams are not the best way to find the velocity of an object where you have a varying force. Okay, let's go ahead and put the values for the various energies into our equation and see what we come up with. We're trying to find the velocity at this point. So here's our initial elastic potential energy, where delta x represents how far it's been compressed. That's over here. We put in our initial height, which we call h0, and then we put on the right side, we have our kinetic energy and we have our potential energy when it leaves the spring up here. We're solving for velocity, so first we put kinetic energy over here. This is the only term that has velocity. And then we go ahead and multiply both sides by 2, take the square root of both sides, and then recognize that h minus h0 is going to be delta h right here. Okay, so we put that into this equation here. So we have the final velocity is the square root of k over m, delta x squared minus 2g times delta h. We now have the equation for the velocity when the block rises a vertical displacement of delta h on this incline, and here it is. But if we're only given delta x, how far we compress the spring, how do we find delta h? Once again, trigonometry comes to the rescue, and you recognize that delta h, which is the side opposite the angle, is just going to be the hypotenuse, which is delta x, times sine of theta. And by using a little math from your geometry class, you can see that this angle theta is the same as this angle theta. What else have you noticed with this problem? Nowhere did we give numbers. We now have the most general algebraic solution for this problem, so whatever spring we put there, whatever mass, whatever displacement, we just have to put the numbers into this expression here, and we're good to go.